Sorting sounds like one job, put things in order. But algorithms see many different jobs hiding inside that sentence. Are the items almost sorted? Are the keys numbers in a small range? Do equal items need to keep their original order? Can we use extra memory? The best sorting algorithm depends on what kind of order problem we actually have. In this video, we will build a sorting map. You will learn the big families: insertion, merge, heap, quick, counting, radix, and bucket sort. More importantly, you will learn the assumptions each one makes, because sorting is not about memorizing names. It is about choosing the right machine for the material. First, sorting usually means ordering records by a key. A record might be a student profile, a transaction, or a search result. The key is the part we compare: score, date, price, name, or priority. This matters because two records can have the same key but still carry different information. Before choosing a sorting algorithm, ask what the input is secretly giving you. How many records are there? Are they random, reversed, or almost sorted? Are the keys arbitrary objects, or small integers from 0 to 100? Do we need stability? Do we have extra memory? These details are not side notes. They are the shape of the problem. A fast sort is often fast because it notices an assumption and uses it instead of pretending every input is the same. Insertion sort behaves like organizing cards in your hand. You take the next item and slide it left until it belongs. It is simple, local, and easy to understand. The important detail is that it mostly pays for how far items are from where they belong. If a value only needs to move 2 spots, the repair is tiny. When the list is small or already close to sorted, that local repair can be surprisingly efficient. The secret strength of insertion sort is adaptiveness. If only a few items are out of place, it does not rebuild the world. It repairs the disorder nearby. That is why practical sorting systems often use insertion sort on tiny subarrays after a larger algorithm has broken the input down. Merge sort is the orderly factory. Split the list into smaller lists, sort those, then merge them back together. The merge step is powerful because two already sorted lists can be combined by repeatedly taking the smaller front item. Every item moves into the output once per level. That gives a dependable n log n shape, and it is naturally stable when implemented carefully. The price is that merging often wants extra working space. Quicksort takes a more aggressive route. Pick a pivot. Move smaller items to one side and larger items to the other. Then repeat inside the two sides. The pivot does not need to be perfect. It just needs to avoid being terrible again and again. If the pivots are usually good, Quicksort is beautifully fast in practice. If the pivots are terrible, the split can become badly unbalanced, almost like peeling off one item at a time. Heapsort turns the array into a tournament structure called a heap. The largest item rises to the top, gets removed into its final place, and the heap repairs itself. Its great promise is worst-case n log n time using only O(1) auxiliary space in the array version. Its trade-off is that it is often less cache-friendly and not stable by default. Insertion, merge, quick, and heap sort are comparison sorts. They learn order by asking questions like, is this key less than that key? In the comparison model, for arbitrary distinct keys, any general-purpose comparison sort has an omega of n log n lower bound in the worst case. Omega means lower bound. No comparison sorter can guarantee fewer than that growth family for all inputs. Merge sort and heap sort meet that wall with O of n log n worst case time. Theta means a tight bound, so their worst case growth is theta of n log n. That wall is not about one bad algorithm. It is about how much information yes or no comparisons can reveal. Here is the intuition behind that lower bound. With n different items, there are n factorial possible sorted orders. A comparison gives only a yes or no answer, so it can only split the possibilities into two branches. To identify the exact order, the decision tree must have enough leaves for all possible permutations. That depth grows like n log n. The wall is not about one bad algorithm. It comes from the information needed to discover an unknown order using only comparisons. Counting sort breaks the comparison barrier by changing the rules. If keys are integers in a small range, do not rely on comparisons to discover the whole order. Count how many of each key exist, compute cumulative boundaries, and use those boundaries to place each record. Its cost is O of n plus k, n is the number of records, and k is the key range. Counting sort is only attractive when k is not huge compared with n. Stable counting sort preserves equal key order by placing records carefully, usually from the end when using cumulative end positions. Radix sort sorts numbers or strings one digit at a time. In least significant digit radix sort, each later stable pass preserves the ordering already created by less significant digits. It requires stable passes and fixed length or padded digits, or a careful rule for variable length keys. Instead of asking which whole key is smaller, it uses digit positions. The algorithm wins when keys have limited length and digit operations are cheap. Bucket sort makes a distribution assumption. If values are spread fairly evenly, put each item into a bucket, sort inside each bucket, then concatenate the buckets. When the bed is right, the bucket stays small. When the distribution is lopsided, one bucket can become the whole problem again. So bucket sort is an average case only when the input supports that assumption. Stability means equal keys keep their original relative order. Stable multi-key sorting works from the least important key to the most important key. To sort by city, then name inside each city, sort by name first, then stably sort by city. A stable sort preserves the existing name order inside each city. Stability is invisible when keys are unique, but very important when sorting records in multiple passes. Another question is memory. An in-place algorithm rearranges items mostly inside the original array. That can matter when data is huge. Merge sort often uses extra space. Heapsort uses very little extra space. Quicksort is usually in place apart from recursion stack space, which is expected O of log n with good pivots but can become O of n without guardrails. Average speed is not the whole story. Quicksort is famous because it is fast on typical inputs, especially with randomization or careful pivot choices. But algorithms used in critical systems also care about worst cases. Heapsort and merge sort offer stronger guarantees when surprises are expensive. Modern computers also reward memory locality. An algorithm that touches nearby memory can run faster than a theoretically similar algorithm that jumps around. This is one reason real-world sorting performance is not explained by big O alone. The shape matters, but the machine still has texture. So choosing a sorting method means asking questions. Is the input tiny or nearly sorted? Think insertion. Need stable predictable n log n. Think merge. Need in-place worst-case guarantee. Think heap. Want practical speed with good pivots. Think quick. Have a small known integer range. Think counting sort. Have fixed length digit keys. Think radix sort. Have fairly uniform numeric data. Think bucket sort. This is why production libraries often combine ideas instead of worshipping one algorithm. They switch tools when the input shape changes. Now the names start to feel less random. Insertion repairs local disorder. Merge organizes by combining. Quick partitions around pivots. Heap repeatedly extracts the champion. Counting indexes by key. Radix walks through digits. Bucket uses distribution. Each one is a different machine for creating order. Here is the mental model. Sorting is not one problem. It is a family of order problems shaped by data size, key type, existing disorder, memory, stability, and risk. The algorithm you choose is a bet about the input. Better assumptions create better sorting. In the next video, we will zoom into quicksort and randomness. We will see why pivots control the whole story, how randomness prevents predictable disasters, and why a tiny random choice can turn a fragile strategy into a powerful practical algorithm.